Okay, so welcome back, everybody. So finally, we are going to see how all of this work to come up with these eigenpairs for a given matrix are going to help us. So finally, we are going to see how to construct. So we saw how to check solutions before. Now this is actually how to find them. So how to construct solutions of the linear system dx dt is equal to ax. And of course this includes some initial condition. And we're going to see this via eigenmethods. Okay, so how does this work? All right, so here's a fact. If lambda v is an eigenpair of A, then if I define the vector x of t to be the scalar valued function e to the lambda t times the eigenvector v, this solves this differential equation. So this linear system, I should say. So this is a solution to star. Now when I say this, I mean it solves this differential equation. Imposing the initial condition comes later, but the point is that this is a solution to this linear system. Okay. Now it turns out that, so notice I said this for a general eigenpair lambda here, so lambda could even be complex. Now I would want this thing, so if lambda is complex, then this thing that I've written here is also complex because I have e to complex number lambda times t, so e to the mu plus I nu times t, so that's a complex valued thing. Now I want all of these things to be real valued, so I have to be slightly careful here. And so in fact, if I say that if lambda v is an eigenpair of A such that lambda is not real, then x1 of t, which is defined to be the real part of e to the lambda t v, and x of 2 of t, which is defined to be the imaginary part of e to the lambda t times v. Both of these are real valued solutions. These are real valued solutions to star. Okay. Now, these are the two biggest facts that allow you to split this down into cases. In the case of a 2 by 2, allows you to split this down into 3 easy cases that will be very familiar to you from what we did for higher order linear equations back in chapter 2. So these are the things that are going to tell me mostly what's going on. I have one other thing that I have to kind of tidy up. Okay, but but this almost does it, right? So what does this mean? And then we'll see some examples that are the same as those examples we did previously. So suppose n equal 2, i.e. the system in question, so A is a 2 by 2, we'll say that it's the matrix, just A11, A12, A21, A22. Okay, and our solution vector is x1, x2. Okay, and then the differential system in question is, the usual. Okay. Then there are three cases. To remind you where these three cases come from, these three cases arise in the exact same way that three cases arose in the second order linear equation case, where the resulting characteristic polynomial for the second order equation was a quadratic, right? Because the order is equal to the degree of the characteristic polynomial for the differential equation. And we know that a quadratic, the case of what kind of roots it has, well, there's three of those cases, right? You can have two distinct real roots, one real double root, or two complex roots in a conjugate pair, right? Those are the three cases. So, similarly, the reason there are three cases is because the characteristic polynomial of A now, right, is this, it's this quadratic here. This is a quadratic, and there are three cases of the roots, right? So roots are either two distinct real roots, two complex roots that we'll label as mu plus or minus I nu, and lastly, one real double root. Okay, so those are the three possible cases here. Okay, now of course roots of this characteristic polynomial are really eigenvalues of A. And so a way of rewording this is to say, well, the eigenvalues of A fall into these three cases, right? Two distinct real eigenvalues, two complex eigenvalues that come in conjugate pair, and one real double root or an eigenvalue with multiplicity 2. Okay. So these are my three cases. So let's do case 1. So let's say that I have eigenpairs lambda 1 v1 and lambda 2 v2 with both lambda 1 and lambda 2 real numbers. Okay. So this is the first case. Okay. Then I have solutions from this previous fact. So I was told that associated to any eigenpair of A solution to this differential system is x of t equals e to the lambda tv. Okay. So this is a solution. So since I have two eigenpairs in this case, I get two of these kinds of solutions, so solutions of this form. All right, and of course, since these are real eigenpairs, right? So both lambda 1, lambda 2, v1 and v2, it's all real numbers involved there. So these vectors all the components of those vectors are real. So this is a real valued solution. I get two of those. So Thus I have two solutions. Solutions of this form are called eigensolutions. So you'll see that reference both in the literature and also just in the online notes. So thus I have solutions, I'll call eigensolutions, x1 of t, which is e to the lambda 1 of t v1, and x2 of t is e to the lambda 2 of t v2. Okay, these are my two solutions. Okay, it turns out, you could check this if you want, I'm not going to check it, but it turns out that these two solutions it turns out that these two solutions are linearly independent, i.e. they form, right, there's two of them, A is a 2 by 2 here, this is the n equals 2 case, i.e. they form a fundamental solution set for this problem that I'm going to continue referring to as star or asterisk, i.e. a general solution to star is x of t is c1 x1 of t plus c2 x2 of t, which I can write as c1 e to the lambda 1 of t times v1 plus c2 e to the lambda 2 of t v2. Okay. All right. This means that the fundamental matrix C of t for star is, remember, the fundamental matrix was defined to be the matrix that had columns made up of the fundamental solution set. So there it is. So this is the matrix that as its first column has e to the lambda 1 t v1, e to the lambda 2 t v2. Okay. So this is the fundamental matrix. Now you might say, what's the matrix exponential from this? Well, here's how I can find the matrix exponential from this. A question: how can I find the matrix exponential from this? The answer is that, recall, there was this fact that if you had a fundamental matrix for the system, the natural fundamental matrix for the system, which was just another way of saying the matrix exponential for the system, this was found to be the fundamental matrix times the fundamental matrix at 0 inverse. Okay, so that's exactly how this was computed. Okay. All right, so we're going to see an example exactly of how this works, but I want to get all of these cases done with so that I can actually carry this out. Okay. So, next case, right? Case 2. Remember, case 1 was the case that I had two real eigenpairs. So case 2 is when I have two complex eigenpairs, right? Two complex eigenpairs. Now, what's cool about this is recall that if I have two complex eigenpairs for a 2 by 2 matrix, I actually know what form they have to take, right? One would be lambda v, and the next one would be the conjugate of lambda and the conjugate of v. So in a sense, both of these eigenpairs are determined from any of the eigenvectors. So if you found one of these eigenpairs, you found both of them by just taking the conjugate. Okay. All right. So in this case, both of these are complex numbers, right? And the v's will definitely contain non-trivial complex numbers. So in this case, from fact 2 here on this first page from today, if I have an eigenpair of A such that lambda is not real, then from that eigenpair alone, I get two real-valued solutions. So similarly, when you have two complex eigenpairs here, which is the case corresponding to two complex eigenvalues in a conjugate pair, really, you only need one of these eigenpairs to form your two solutions. The other eigenpair will form identical solutions. Okay, so in a sense, having one of these tells you both of the story. It's actually enough info to tell you everything you need just from this one eigenpair. So we'll just pick this one. So in this case, we have two real valued solutions to star, which are x1 of t equals the real part of e to the lambda tv, and x2 of t is the imaginary part of e to the lambda tv. So those are the two. Now, if we say that lambda is mu plus I nu, right, then what does this become here? Well, this would become the real part of e to the mu plus I nu t times v. This will become the imaginary part of e to the mu plus I nu times t times v. Okay. So what does this lead me to if I rewrite both of these, right? This would be the real part of what? This would be e to the mu times cosine of nu t plus I sine of nu t times v, and the imaginary part of e to the mu cosine of nu t plus I sine of nu t. Now, it doesn't really make much sense to go further than this in writing. In fact, there's an argument to be made that you should just remember this this first part. I'm just reminding you, of course, that when you're raising e to complex number, you get this thing, right? So we dealt with this before back in chapter 2. But it doesn't really make sense to go much further because the components of v, some of them are going to be complex. So like the actual form this thing ends up taking, of course, depends on which of those is complex. And remember, you're taking the real and imaginary parts of those. So we'll see how this works in the examples. Okay, but that's the idea here. Okay. All right, and so it turns out, just as before, it turns out that these are linearly independent. What does that mean? It means that their Wronskian is non-zero, i.e. they form a fundamental solution set. For star. Thus, a general solution to star in this case is x of t, which is c1 x1 of t plus c2 x2 of t, which is c1 times the real part of e to the lambda t times v, plus c2 times the imaginary part of e to the lambda t times v. And that is as far as it makes sense to go. Thus, the fundamental matrix of star is C of t, which is the matrix that has these two members of this fundamental solution set as its columns. Okay. And I find the natural fundamental matrix, or the matrix exponential, in the exact same way. Okay. All right. And so, now for case 3. This is kind of sort of the trickiest of these cases. The reason why is the same reason that it was tricky in chapter 2 stuff. Right, so the remaining case is what happens when we have a single real eigenpair for an eigenvalue that has multiplicity greater than 1. In this case, it can only be 2 if it's greater than 1. So case 3, a single eigenpair, a single real eigenpair lambda v corresponding to a double root lambda of the characteristic polynomial. Now, the fact that this is a single real eigenpair is the issue here. Okay, so why is this an issue? Because I already know from this very first fact that I wrote down on this very first fact that I wrote down on the first page from today, that if you have an eigenpair of A whatsoever, this is a solution to star. So I already have one solution. Okay, so I already know that x of 1 of t, which is e to the lambda t times v, is a solution to star. So I have one solution. I know that's not enough. I need two linearly independent solutions, right? I need two linearly independent solutions, two solutions that form a fundamental solution set. Okay. But I only have a single eigenpair, right? In the case of two distinct real eigenpairs, I had that second eigenpair to give me my second one. From the complex case, from a single eigenpair, I got both of them, right? So I didn't need anything else. But here, this is an issue. I only have one real eigenpair, and from that, it seems like I only get a single eigensolution, and that's it. Okay. So then, how do I get my second solution? So it turns out that x sub 2 of t defined to be e to the lambda t times w plus t e to the lambda t times a minus lambda I times w is going to work where w is any vector in R2 that is not proportional to the eigenvector. When I say will work here, what I mean is that these two taken together form a fundamental solution set. So these two are linearly independent, and that does it. Okay, then a general solution in this case is x of t defined to be c1 x1 of t plus c2 x2 of t. I'm not going to write the rest out, but this works in the exact same way. Fundamental matrix works in the same way. Finding the matrix exponential works in the same way. Okay. All right. So there we go. Now, what is it that's going on here? Notice that what's going on here is very similar to what happened in the chapter 2 case, right? So in the chapter 2 case, what we did when we came across a root of the characteristic polynomial that had multiplicity, let's say multiplicity 2 in the n equals 2 case. So in that case, it turned out that, the trick there was instead of using e to the lambda t, you couldn't just use e to the lambda t again because the Wronskian would be 0. You added a t here, right? So you added a t there, and you considered t e to the lambda t, and that turned out to work just fine. Now you can't quite do that here. There's this little extra song and dance you have to do, okay? But this works in a way that is analogous to what we had to do in the chapter 2 case. All right. So finally, let's see some examples. And what better place to start than our favorite? All right, so the example, so find the general solution. So this is the first part. Find the general solution to dx dt is equal to ax, where a is equal to 3, 2, 2, 3. And secondly, find the matrix exponential e to the ta. So how do I solve this? Okay, so first recall A has eigenpairs. We found these in yesterday's lecture. So in the previous lecture, we found that A has eigenpairs. There's 2 of them. The eigenpairs are 1 and 1 minus 1. I might have said minus 1, 1 yesterday, but that's fine. 1 minus 1 works perfectly fine because I've just scaled that by minus 1 instead. Okay, so that's perfectly fine. And the next one is 5 with eigenvector 1, 1. So there's the eigenpairs this thing has. Thus, by our recipe, let's just remember, hasn't been that long, but let's remember anyway. So our recipe is we have 2 real eigenpairs, then I get 2 solutions that form fundamental solution set, which is, so first one is e to the lambda 1t v1, second one is e to the lambda 2t v2. Okay. All right, so thus by our recipe, we have eigensolutions which is x1 of t, which is e to the 1 times t, so e to the t times 1 minus 1, and x2 of t is e to the 5t times 1, 1. This is e to the 5t times 1, 1. All right. Let's check that these are actually linearly independent. Let's check that they are linearly independent. Normally, you do not have to do this. Okay? You don't have to do this check unless I specifically ask you. Okay? So unless I specifically ask for it, you don't have to do this step, but I'm going to do this anyway. So I want to compute the Wronskian of x1 of t, x2 of t, which is simply the determinant of, and of course, well, if I want to do this, I could always do this at a single point. So I could do this at the point 0. So I could do this at 0. So this is by that fact that I didn't prove, but I quoted Abel's theorem, which says that if it's non-zero at a single point, it's non-zero everywhere. So just do this at 0. This would be the determinant of the matrix 1 minus 1, 1, 1. Okay, what is this determinant? This is 1 times 1 minus minus 1 times 1. So 1 plus 1 are 2, which is non-zero. Okay, so they are in fact linearly independent. Okay. Thus, the general solution is x of t, which is c1 x1 of t plus c2 x2 of t, which is c1 e to the t times 1 minus 1 plus c2 e to the 5t times the vector 1, 1. Of course, you could multiply these out if you really felt like it, and that's perfectly fine. In fact, if you did that, let's rewrite this as a vector equation like this. So this is x1 of t, x2 of t, right? That's what the left-hand side is. On the right-hand side, this would be a vector with two components. This would be c1 e to the t plus c2 e to the 5t. That's in the first slot. In the second slot, this would be minus c1 e to the t plus c2 e to the 5t. So that would be this thing written as a vector equation like this. You don't have to write it like this. You're perfectly happy writing it in this form. Okay, but this is what is being said. Okay. Now, what other quantities can I come up with? So this is finding general solution. Boom, there it is. I want to find the matrix exponential. Before I do that, I want to write out the fundamental matrix. So fundamental matrix for this system is C of t, which contains x1 and x2 as its columns. Right? Well, here's x1, here's x2. So its two columns are e to the t minus e to the t and e to the 5t, e to the 5t. So that's the fundamental matrix. Recall that the matrix exponential, e to the ta, is found by taking fundamental matrix for A and multiplying it by its inverse at 0. Okay. Thus, I need to find this. Well, what is C of 0? C of 0 is 1, 1 minus 1, 1. Okay. How do I compute the inverse of this? Recall, if A is the 2 by 2 matrix A, B, C, D, then A inverse is 1 over the determinant of A, so 1 over AD minus BC, times, swap the main diagonal, negate the off diagonal. This is how I compute the inverse of a 2 by 2. So then C of 0 inverse is 1 over the determinant of this. So 1 over 1 times 1 minus 1 times minus 1. So 1 plus 1 or 2. So this is 1/2 times the matrix. I swap these two. That does nothing. I negate the off diagonal. So this is minus 1. This is 1. Okay, so this is the matrix 1/2 minus 1/2, 1/2, 1/2. Okay. So this matrix exponential is C of t, which we found to be, reading row-wise, e to the t, e to the 5t, minus e to the t, e to the 5t. This is times C of 0 inverse, which we computed to be 1/2 minus 1/2, 1/2, 1/2. Okay. And then doing this matrix multiplication, so what do I get here? This would be 1/2 e to the t plus 1/2 e to the 5t in the first slot. In first row, second column, I take first row, transpose it, dot it with second column. This would be minus 1/2 e to the t plus 1/2 e to the 5t. Second row, first column would be minus 1/2 e to the t plus 1/2 e to the 5t. And second row, second column would be 1/2 e to the t plus 1/2 e to the 5t. So there it is. Okay, an alternative form, once you found this, an alternative form of general solution is x of t is e to the ta times c, or c is the vector of constants, so this is e to the ta times the vector c1, c2. So this is another way of writing the general solution. All right, this is actually one of our original motivations for finding the matrix exponentials, because it just allowed writing the general solution as matrix exponential times this thing. And you can check yourself that this indeed forms general solution. Okay, this here, if you do this matrix multiplication, is the same as this. Okay. All right. So that is how that works. Let's do another example. Okay. So find a general solution to dx dt is equal to cx, where C is our favorite matrix with complex eigenvalues, which is 3, 2, minus 2, 3. Okay. And secondly, compute e to the tc, the matrix exponential of c. Okay. So to do the first bit, recall C has eigenpairs we've already found last lecture. These eigenpairs are 3 plus 2i with eigenvector 1i, and 3 minus 2i with eigenvector 1 minus I. Now, I think when we did this in the last lecture, these eigenvectors looked a little bit different. So, I want to do a little aside, right? This is a little aside here. This bit that I'm about to do has nothing to do with finding this general solution. This is just something to hopefully help restore your sanity if you are trying to do some of these problems and you end up getting a result that you're pretty sure is wrong because it looks different than what you should get. So this is going to help you see that sometimes it looks different, but it's really not. So for instance, say we know that 1i is I should say is an eigenvector of C. Of course, it's associated to 3 plus 2i. We forget that, right? So associated to 3 plus 2i. Well, then any constant multiple of 1 plus I is, or sorry, not 1 plus I, it's just the vector 1i, is also an eigenvector of C for the same eigenvalue. But, right, when I say constant multiple, so of course saying this is not controversial at all. You already know that, right? So I went over this a couple of times, that you have an eigenvector, you can scale it by constant, and you're good. But, right, typically when you hear the word constant, what you're thinking of in your head is a real number, right? A scalar, a real number. What we mean here, though, in the context of a vector that can have complex entries, is that this can even be, so can even, just in this case, be a complex constant. So, for instance, I times 1i. Well, what does that look like? This. So this is also an eigenvector for C, associated to 3 plus 2i. Okay, so this is an example of the kind of thing that you can get, whereas, so if I had written this as 3 plus 2i, I minus 1, and that may be what I wrote yesterday, I can't remember. If I had done that, this is the same as having 1i here. So you see how it doesn't look like these would be the same? You're not used to thinking of multiplying by a complex number as being an example of scalar multiplication or of constant multiplication. But it is in this case. So it is an example of that in this case, and this exactly shows why. I times 1 is I times I is minus 1, right? So this is the kind of thing. So I minus 1 is exactly the same as an eigenvector as 1i. Okay, so there's that little tricky thing that can go on. This can confuse you sometimes because if you're comparing answers either with the solutions in the online notes or with your classmates, this is a thing that can happen depending on choices you've made in the problem. This is a thing that can happen that it might look like you and your classmates have set different answers, but it's not. It's actually the same thing. Okay, so I just wanted to do that little aside. Okay, so back to what I was doing. Recall that C has two eigenpairs look like this. Okay, thus by our recipe, let's remind you what that recipe is. So case 2, we had two complex eigenpairs. Actually, I only needed an eigenpair for one of these to generate my solution, so I had the eigenpair for both. I can use either one of these I want. I'm just going to use this one. So by this recipe, I only need to use one, and we'll say that I'm using 3 plus 2i and 1i. This means that by our recipe, my fundamental solution set, I'm not going to check it this time, is x1 of t, which is the real part of, again, we're using the eigenpair 3 plus 2i and 1i. Okay, so this is the real part of e to the 3 plus 2i times t times the vector 1i. So what is this? This is the real part of, let's say we have e to the 3t here times times cosine of 2t plus I times sine of 2t times 1i, which is the real part of, let's just write it as a vector if you like. So this would be e to the 3t cosine of 2t plus e, or I times e to the 3t sine of 2t in the first slot, because I'm just multiplying it by 1. In the second slot, this would be I e to the 3t cosine of 2t minus e to the 3t, because this is I times I, so I squared, which is minus 1. So this would be minus e to the 3t sine of 2t. Okay. Now, you may be able to figure out what the real or imaginary part is of this quantity without, so of this thing, without writing this out. That's perfectly fine. This helps us to see what it is that's going on here. Also, we have to do this, like this is the same quantity we're writing, whether we're taking real or imaginary part here. So we have to do this in the second part anyway. So this is the real part of this, which is e to the 3t cosine of 2t. It's the real part of this slot. The real part of this slot is minus e to the 3t sine of 2t. So that's x1. And x2 is the imaginary part of this same thing. Well, I don't have to write all this out again. You see how depending on which slot has an I in it, or what this thing is, actually affects what you get here. So it's best to just remember this basic thing and then do this algebra. So this is the imaginary part of this same quantity. So this would be e to the 3t sine of 2t. There it is. And the imaginary part of this piece is e to the 3t cosine of 2t. Okay, thus my general solution is x of t, which is c1 x1 of t plus c2 x2 of t, which is c1 times e to the 3t cosine of 2t minus e to the 3t sine of 2t plus c2 times e to the 3t sine of 2t e to the 3t cosine of 2t. Okay, now we're almost done with what we were asked to do. Now, the fundamental matrix is the matrix C that has as its columns the members of the fundamental solution set. Well, let's bring them back. Right, so there they are. Here's x1, here's x2. So that's the first column, that's the second column. So this is the matrix whose first column is e to the 3t cosine of 2t minus e to the 3t sine of 2t. The second column is e to the 3t sine of 2t, e to the 3t cosine of 2t. Okay. So then this is the fundamental matrix. The natural fundamental matrix, or the matrix exponential. So the matrix exponential e to the tc is c of t times c of 0 inverse. So in order to do this, let's find c of 0. So what is this? So I have e to the 0 cosine of 0, so that's 1. E to the 0 sine 0, that's 0. Minus e to the 0 sine 0, that's also 0. And 1 times 1. So the determinant of this, of course, is 1. This is the identity matrix. This is the 2 by 2 identity matrix. It is its own inverse. You can check that yourself. But the identity matrix is its own inverse. Okay. And so c of 0 inverse is just c of 0, it's just 1, 0, 0, 1. And so what is this thing? This matrix exponential is this thing times its own inverse, which is the identity matrix, which is, it doesn't matter what side this happens on. This is actually just c of t, which is e to the 3t cosine of 2t, e to the 3t sine 2t minus e to the 3t sine 2t, e to the 3t cosine 2t. So there it is. Okay. All right. So that's that for that example. Now, let's do our last example. Okay, so let's do our last example and construct matrix exponential for it. And then we will be done with this. So last example. Okay, so 1, find the general solution. 2, dx dt is equal to bx. Okay, where b is our favorite matrix that has a double eigenvalue. So 4, minus 1, 1, 2, reading row-wise. Okay, recall B had eigenpair that was 3, 1, 1. So remember that. So secondly, find the matrix exponential e to the tb. Okay. All right, and so from our recipe, now our recipe in this case was a little bit more complicated. So we got the normal, so we got this normal expression where the first eigensolution was the usual thing. It's e to the lambda t times the eigenvector. Okay, but then the second solution was slightly different here, right? So we know from the recipe, yeah, x sub 1 of t is easy to find. It's just e to the 3t times 1, 1. Okay. All right. Now, to find x sub 2, I need to pick any vector that is not proportional to v. V is 1, 1 here. So I need to pick any vector that is not a scalar multiple of v. Well, that gives me a huge amount of choice. So choose w to be 1, 0, right? There we go. The vector 1, 0 is definitely not a scalar multiple of the vector 1, 1. Okay. Then we can write this x sub 2 of t as e to the 3t times w times 1, 0 plus t e to the 3t times the matrix b. Maybe I should go ahead and maybe I should actually do this separately. So I'm going to write this as b minus 3I times w, which is 1, 0. So let's do b minus 3I separately. So what is b minus 3I here? Right, that's the matrix b times, or minus 3 times the identity. So this would be 4 minus 3 in this slot, so that's 1. Minus 1, 1. And this would be 2 minus 3 in that slot, so minus 1. Okay. Well, what would this matrix times the vector 1, 0 be? All right, so this is how we computed this. I'm going to get rid of that so I don't have to write anything wrong here. So this is 1, 0. What would this be if I multiply those two together? So I should get a vector. My vector is going to be 1, 1. That is what I'm going to get there. So this is e to the 3t times the vector 1, 0 plus t e to the 3t times the vector 1, 1. And that's where I'll stop for now. Okay. So there's our two things here. Okay. Now I could rewrite this as like e to the 3t times a single vector. Maybe I'll do that. So maybe it makes sense to do that. So let's rewrite this as so if I combine these, right, this would be like e to the 3t plus t e to the 3t, and that would be 0 plus t e to the 3t. So you could write this as e to the 3t times the vector 1 plus t. There, that's where I'll stop. Okay. So there's my two eigensolutions. All right, thus, the general solution is x of t, which is c1 x1 of t plus c2 x2 of t, which is, so this is c1 times e to the 3t times 1, 1 plus c2 times e to the 3t times 1 plus t. Okay. Now, I need to find the matrix exponential. So my fundamental matrix C of t is what? It's the matrix containing the eigensolutions, or the fundamental solution set. So this is the matrix e to the 3t, 1 plus t, e to the 3t, e to the 3t, t, e to the 3t. You can factor out an e to the 3t here. It's fine either way. Okay. Thus, the matrix exponential e to the tb is what? This is c of t times c of 0 inverse. What is c of 0 here? This is the matrix 1. So this is 1 times, this would be 1 plus 0 times 1. So this would be 1. Here this would be 1. And here this would be 0. Right? Okay. And so what is c of 0 inverse? This would be 1 over the determinant of this thing. So 1 over determinant. Determinant is 0 minus 1, so this would be 1 over minus 1 times, I swap the main diagonal, negate the off diagonal. So this is what I get. So then what I end up with is 0, 1, 1, minus 1. This is the inverse. You can just check that that is in fact the inverse of that matrix. So then this is going to be c of t. So this is going to be c of t, which is here, times this matrix. So this would be e to the 3t times the matrix 1, 1 plus t, 1, t, times 0, 1, 1, minus 1. So this is going to be e to the 3t times, what is this matrix? So this would be first row, first column, so 1 times 0 plus 1 plus t times 1. So that's 1 plus t here. In the first row, second column, this would be 1 times 1 plus 1 plus t times minus 1. So 1 minus 1 cancels, and I'm left with minus t here. Okay. In this slot, this would be second row, first column, so 1 times 0 plus t times 1, so this is t. And then in the very last slot, second row, second column, this would be 1 times 1 plus t times minus 1, so 1 minus t. And that's it. So that's my matrix exponential. Okay. All right, so that is how to deal with all of this. That is how to deal with every single type of 2x2 problem like this. So this is how to generate the general solution following this recipe using the eigenmethods. Okay. So now you have all the tools to deal with any problem that asks something like that. Okay. Now, our next topic is linear planar systems, which is going to use what we just did, okay, coming up with these general solutions by the methods of eigenvalues, eigenvectors, so these eigenmethods, to actually analyze what these solutions are doing, right? So what is the idea here, right? The idea now I want to graphically analyze solutions to these systems in a way that is analogous to what we did in Chapter 1 with phase portraits. So remember, I was able to analyze solutions to first order equations, specifically first order autonomous equations, um, using phase portraits by drawing this one-dimensional phase line. And due to existence and uniqueness of these things, this led me to be able to say a bunch of things about how the long-term behavior of the solution had to go. So, for instance, you recall in chapter 1, if I knew, that I had, so recall from chapter 1. If I had a phase line for some problem that maybe looked like this, okay, and maybe this is what it looked like. Okay, so here's my stationary points, right, and here's the behavior indicated by the sign of the derivative between these stationary points. All right, so for instance, these arrows to the right here indicate that if these are my points, so this is 0, this is -1, this is 1, then, to the right of -1, these arrows would indicate my solution is going off like to infinity. The fact that this solution is 1, though, means that I can't have a solution like a solution in the plane that crosses this, right? So in fact, these three things give me horizontal lines, right? So we'll say there's my three horizontal lines. So here's the line y equals -1. Here's y equals 0. Here's y equals 1. These stationary points corresponded to lines that other solutions could not cross, right? So, and any initial value here had to do something like this, and they weren't allowed to cross or touch, and this was because of the existence and uniqueness theorem. Specifically, uniqueness told you that you couldn't cross or touch, because that would signify being able to choose a different initial value for which the solution emanating from that value would not be unique, because they touch there, right? And you would have two distinct solution trajectories emanating from the same point. That's no good. That's not uniqueness, right? So we thought about this as like, demarcating the plane or marking off the plane, dividing the plane. Once you had these horizontal lines, any kind of behavior that your solution to your differential equation had, it was bounded between these things, right? It couldn't cross or touch them. So that was a huge benefit for us to being able to analyze these things, because this constrained the behavior in such a way that let us figure out what it was that was going on. So I wanted to do something like this for these first order systems. Okay, so I want to do this for these first order systems. So what does that mean? So a first order system, we can recast the thing that we've been doing this whole time as the following. Instead of labeling the solution vector x of t as x1, x2, to kind of help your intuition, let's label it as x of t, y of t. Right? A will still be my 2 by 2 matrix, A11, A12, A21, A22. Okay. So then, doing that, right, then a solution to this system is x of t, which is the vector that has component functions x of t, y of t, which I can think of as the ordered pair x of t, y of t, a parametric curve in the plane. Right? Maybe it looks like this. Right? So that a single point on this thing is an x of t, y of t. Right? And as t progresses, I go, say, along this curve in this way. Okay. So any solution to these differential systems that we've been working on all this time for the last 5 lectures or so can be thought of as this parametric curve in the plane, or a trajectory as it's called, or orbit is another word for this. And the reason for that is simple. It's because, you think how I think about an orbit typically, or more generally like a trajectory, is just some path that's traced out in the plane here, right? So due to existence and uniqueness theorem, specifically the uniqueness bit, for linear systems. So what is this? First of all, what am I saying? So how many trajectories are associated with a linear system? Typically, well, infinitely many, right? So there's infinitely many of these. Maybe this is what they look like, right? Maybe here's another one, and here's a few more. Maybe here's one. Maybe here's another one. But the very important thing is, due to existence and uniqueness theorems for linear systems, these trajectories for the same system cannot touch or cross one another. Okay. And this is, again, due to uniqueness. So the usual way of thinking about this is the following. I'm looking for general solution to this. General solution is this, so, any solution to this thing is some parameterized curve. Different choices of C1 and C2 give me different families of parametric curves like this. But these families are not allowed to cross or touch, because that would indicate a failure of uniqueness of solutions to this system. And by the existence of uniqueness theorems, we know that we have these. So because of that, what this means is that we have constraints posed on how trajectories to a system can look. Okay, so for instance, this is a valid picture, but like this, for instance, would not be a trajectory that meshes with this. It would not be a trajectory of the system, because this sort of thing is just not allowed. Okay. So our next goal is to understand the structure of these trajectories for the system. In fact, this is going to be the last thing we spend any effort on for the remainder of the course. There's 4 more lectures we have to go over, and in those 4 lectures, I will basically start from trying to understand these linear system trajectories, and we'll progress through to seeing how this ties in with helping us understand more general types of systems. So specifically, we are going to talk about some nonlinear systems and how to deal with those things. Okay, so that's where we're headed. We got 4 more lectures. Now that we're done with this stuff, I can finally assign you some homework on it. So you have 1 more homework that's just general problems. You have a midterm next week, and you have a MATLAB due tonight, although I'm going to send out an announcement later saying that I'll be flexible with the MATLAB deadlines. You'll have another MATLAB that I'll assign that will be due next week, and then you'll have final exam next week. So it's a lot of stuff coming up in the next week. So please, if you have any questions, let me know. So anyway, that is that. I'll let you know in the next, next problem session, or next homework, or office hours, I should say, is going to be next Tuesday. So next Tuesday, right after lecture, I'll do this. Okay. So anyway, that is that. I will see you all later. See you all on Tuesday.